Hello everyone, this P9 module is an overview of flux core arc welding and hard facing. Page 3 to 9 in your book is review of P6 wire, which is in your foundations module. When cylinders for welding and cutting are being used, it is preferred to store them in shaded areas out of direct sunlight and away from hot work. As the temperature in the area increases, the cylinder pressure will rise. If a cylinder was to be heated to 500 degrees Fahrenheit, it could increase the cylinder pressure by over 100%. When using carbon dioxide as a shielding gas, high arc energy can break the gas down into carbon monoxide. Not only is this toxic to your health, it affects welding by allowing small amounts of atmosphere into the weld area. This is why most wires designed to be used with CO2 have additional deoxidizers to counteract the gas loss. And for all you close welders out there, back your head out of the smoke to reduce exposure. Mode of metal transfer depends on power supply, filler wire type and size, material thickness and composition, and shielding gas being used. At lower settings, short circuit metal transfer occurs, filler wire contacts the base metal, uprises in current, and short circuits, pinching off a drop of molten weld metal. This process repeats itself continually from 20 to 200 times per second. As current and voltage increase past short circuit, globular transfer is produced. The metal droplets are gravity fed across the arc. The molten droplets are usually larger than the wire diameter, which can cause problems with spatter. As settings are increased on a reverse polarity with at least 80% argon, the molten droplets transition from being big and irregular to droplets that are smaller than the wire diameter and crossing the arc at a high velocity. A little review on need-to-know power source information. Direct current, constant voltage power sources are used for wire processes and are paired with a constant speed wire feeder. The volt-amp curve is relatively flat compared to constant current power sources. And a reminder that constant current power uses a variable speed wire feeder. Constant voltage power source is self-correcting in arc length and by affecting the amperage. As you get closer to the work, amperage increases to help burn the wire faster. As you get farther away, the system reduces amperage to control the slower burn-off rate of the wire. The voltage drop over 100 amps is calculated as slope. This reduces spatter by limiting high current surges with short circuit transfer. This is a reference to the volt-amp curve and the relationship between volts and amps. A few notes. Variables for flux core. The power source and wire feeder are the same as gas metal arc welding. The flux inside the tubular electrode helps strengthen, protect, and improve shape of the weld. And the major source of contamination is atmosphere. Flux core has calcium, potassium, silicon, or sodium added, which are similar to the slag formers used in low hydrogen electrodes. Slag slows the cooling rate, protects the cooling weld from oxidation, and improves weld bead shape. Here we have the three main variables. Pre-selected is all about selecting your wire type and everything that goes with it, roll type, gas, and whatnot. Primary adjustable is setting your machine, voltage and amperage. And secondary adjustable is the welder's skill to lay a decent weld, which is most important. If your stick out is too close, you can snag your nozzle in the weld or vaporize the oxidizers in the wire and get worm tracks. If your stick out is too great, you decrease amperage and lose gas coverage. If there's slag, you drag, also known as the backhand technique, and welding too fast has its own issues as well. Welding current is directly related to wire feed speed. Increasing current puts the wire closer to the base metal, which increases deposition and penetration. Arc voltage is adjusted on the machine. Increases in volts will make a flatter, wider weld bead, and too much volts creates an uncontrolled arc length, leading to excessive spatter. Pushing versus pulling, also known as forehand and backhand welding. You get less penetration when pushing and a flatter weld bead profile. Pulling increases penetration and builds up more metal, giving you a higher, narrower weld bead. One thing that is not talked about much is perpendicular welding and its benefits from both forehand and backhand. We'll cover that stuff in the shop. The contact tip is most important because it transfers all the power to the wire. If it gets worn, you get problems. Sometimes if it's worn too much, the wire will jump around and arc out inside, tack welding itself inside the nozzle and then bird caging on you. Always make sure the wire is centered in the nozzle. This will keep the wire in the shielding gas zone. A tapered nozzle provides better weld visibility, and nozzle size depends on current levels. Few welding defect corrections. Incomplete penetration. Primary cause is not enough current or wire feed speed. For electrode stubbing, you got too much wire, decrease the wire feed speed. Wagon tracks is from tip to work distance too close or shielding gas flow rates too high. A few more notes here for you. Pause as you need to. Shielding gases. CO2 is the least expensive and only reactive gas used on its own without the addition of argon for welding. Low carbon and low alloy steels utilize this gas. Since CO2 reacts with the weld, creating more heat energy, at higher current levels, metal transfer is affected, making the transfer of metal erratic, causing lots of spatter. The bottom 2/3 of a carbon dioxide cylinder is liquid. If not changed out at 150 psi, there is a chance of drawing liquid through the regulator and freezing it up. Argon is the most commonly used shielding gas. It's a great base for many gas mixtures. This gas is inert and will not combine with materials in the weld zone. It is widely known for its arc stability characteristics. A few more notes here. Moving on to filler wires. Flux core electrodes are designed to meet industry standards. Most are machine made by pouring flux into a U-shaped sheet, then squeezing the sheet shut and passing it through a series of dies to get the desired size of wire. Two main types of flux are rutile and basic. Rutile is also known as titanium dioxide, and basic flux is also known as low hydrogen. Rutile designed electrodes are great over a wide current range. All position weldability makes it more welder friendly. A basic electrode has great mechanical properties, but must be in close current ranges and does not handle out of position welding too well. Here is a flux core electrode classification example. E is electrode, 7 indicates tensile strength, but can be either CSA or AWS. Next is position designator. T indicates the wire is tubular, filled with flux. And 10 is current, polarity, and slag system. A shielding gas indicator can follow the slag system. M is a mixed gas, C is 100% carbon dioxide. And CH, beyond that, would be controlled hydrogen, which reduces moisture content in the weld metal. Bonus for red seal prep. Metal cored electrodes are quite similar to flux core, except that they have a C indicating it is a cored wire with metal powder and no fluxing ingredients. Without any flux or slag formers in the wire, there's no slag to remove on these welds. Usually an argon-rich gas mixture is preferred. and you weld this stuff pretty hot at high current levels. Quick summary here. The next posted slide is short, but will cover the hard facing materials in your P9 flux core arc welding module.